All right. Hi, everybody. Welcome back to the Broad's Machine Learning for Health seminar series. So today we have Dr. Tristan Naumann, who is a principal researcher in the Real World Evidence Group at Microsoft Research's Health Futures. And so his research in particular explores the relationships in complex and unstructured health data using techniques from natural language processing and unsupervised learning. And in addition, he served as the general chair and in other roles at several conferences, including NeurIPS, CHIL, and ML4H. And so today his talk is entitled Real World Evidence in the Age of Generative AI.
Yeah, thank you so much, Danielle, and also Mahtaz for sort of connecting us initially as part of this as well. Yeah, so I'm Tristan. I'm going to talk with you all about sort of real world evidence and in this sort of newfound landscape that we found ourselves all in collectively. But maybe I'll sort of start by saying I'm a researcher over here in Health Futures at Microsoft Research, and I'm happy to answer sort of questions for many of you about that as well, since I think there's not maybe broad awareness that we're doing as much research in the healthcare space as we are. But I thought maybe I would sort of get started today talking a little bit about how I ended up here as well. So I think this is maybe one of many different examples that I recall when I sort of first started looking into this broader context of healthcare. And I think one of the things that really disturbed me about it was, in the sort of like ideal world, obviously we hope that everybody receives sort of a treatment and sort of sees the intended effect from that treatment. But that was very clearly not the case. And I think this specific example was really particularly concerning because it looked to non-responders for some of the top prescribed drugs, right? And it looked and found that there were about 80%. And so, I mean, minimally, this is wasted healthcare spend. But I think this is actually a great example where in the healthcare system that we have currently, we might think that we are actually, doing a very good job of, prescribing and sort of taking action that confers benefit to patients. But in fact, if they're just getting side effects and not the intended effect, we're actually doing harm. And so it really had me thinking quite a bit about, if we have examples like this, and again, this was sort of just one of many, what are we doing from an evidence basis to really make sure that we're actually improving the state of care? And that sort of is a hop, skip, and a jump, perhaps, over to something like real world evidence, where it really stands to sort of fulfill this vision. And the core idea is actually incredibly simple, which is we actually already collect tons of data in healthcare. Increasingly all this data is getting digitized. At this point, I would argue, certainly at academic medical centers, it's already digitized. And so, what is sort of the like free lunch that we might be able to get from building a learning system around all of this data? Can we actually distill sort of insights at scale? And not to say, of course, that it would surpass or supplant sort of the existing gold standard of evidence generation in medicine, the randomized control trial, the RCTs, but what can we sort of use it for to sort of complement that existing evidence basis? And so when I started approaching this space, really came at it from this angle of natural language processing, which maybe for many of us seems like an odd place to start. But the intuition or the motivation perhaps was that it was actually key to unlocking sort of the future of medicine. There's a lot of things that we know collectively are really important in a medical context. We know, for example, that heart rate is a very important measure of cardiovascular health. We have collectively as a society instrumented ways to measure that with very high frequency, very high fidelity. All of the other stuff where we think it's important just, to keep in mind for a future version of ourselves or somebody else in the care team, all of that ends up just thrown into notes. And so the idea, initially was really, how can we leverage that information and really expand the horizon of the medicine that we're able to procure and, discover and derive for patients? That in turn led to sort of this exploration of multimodal modeling, in part because, as much as from a machine learning angle, many of us like to sort of silo ourselves around the modalities that we're comfortable with, and, develop specific techniques within that area. Patients generate lots of different types of data, and they do so in this way that specifically is really important to leverage across, to have sort of like a higher level sort of cross view across all the information they're generating. It doesn't make sense necessarily to say, hey, I'm just going to ignore a third or more of the data points that a patient has because I'm actually only comfortable working with text. Like that's not a very good thing to do. And so I think what's sort of interesting about this space that we've sort of found ourselves in, and maybe to sort of refer back to the sort of intro slide, what generative AI might allow us to do is it really might allow us actually some early opportunity in achieving some of these sort of multimodal goals that we've had for a long time, and allow many of us to work across some of these different silos and different modalities, in part just because some of the underlying architectures that we've discovered in specific modalities work actually quite well across several different modalities. And so again, I think this is really this notion that, if we really want to, not just sort of with the initial motivation of expanding the sort of horizon of medicine, but we really want to unlock these new opportunities. We really need to leverage information from across all these different points. And I think this is a really interesting time, like where this is really a time where many of us, I think over the past few years, have been rethinking what does it look like to do machine learning? What does it look like to do AI for health specifically? And I think certainly in the NLP space, as we've seen the evolution of large language models, suggests it's a really pivotal time for NLP in health. But more broadly, we see a lot of these things that have brought up sort of debates, even, a lot of them maybe around USMLE and how do we actually measure performance? Is it meaningful to be able to score very well on some of these tests that doctors are taking? There's certainly arguments from doctors and clinicians saying, no, it's really not very, it's not super interesting because a lot of care is learned as sort of this in practice rather than sort of just the tests that we take. But I think there are two things that have really, stand out to me at least over the past few years and what this evolution has looked like. I think the first one is whether or not something like USMLE in its own right is an important benchmark is somewhat incidental to this idea that if you had asked me 5 years ago, can you do something that will do UMSLE? Like, can you make a model that will do USMLE? I probably would have given you a very hedgy answer. It could have been sort of like a grant proposal with multiple aims of how we're going to break down this problem and do it with a bunch of different students focusing on different parts. And now it's table stakes for every model. No matter what it is, it's sort of just like a baseline performance. Let's check it as a regression to make sure we don't go too far backwards, right? And I think that's actually a pretty significant change. The second one is really this, idea that this mechanism of prompting actually can bring into this overall experience more people than have been available previously. So if I think back to a lot of the exploration I did with clinicians, there was sort of this, constant collaborative back and forth where they were asking me for something, I would go and do some analyses, we'd share some of the results. And this actually allows a lot of MDs to ask some of those same questions much more directly. If you can actually just sort of work through a bunch of data using various prompting techniques, or extract some new form of information using those same techniques, it really can tighten some of that loop as well. Not to say, of course, that it's perfect or anything like that, but really just to say it's opening up some of these new opportunities already. And so I think for today, I was really impressed because I was thinking about all of the work that our group has done and all of the broader work that's going on in the space. But I decided to sort of maybe focus on sort of two areas of research that I think are particularly exciting. The first one really around this idea of LLMs and their sort of innate ability to structure information, sort of a concept that we've been evolving into something called universal abstraction. As discussing a little bit earlier, I was actually just checking to see, did things land on archive? I think the corresponding paper that I'll reference here landed on archive perhaps yesterday. So should be also available. And the second is really maybe this expansion toward sort of multimodality and some of the proof points that we've been working on and developing there as well. And then also, again, across the broader field. I think, maybe as I dive into this area of, what it means to do sort of abstraction in general, also maybe by way of story, I think our group really started thinking about this more from a biomedical context. And we started thinking about it from this standpoint of clinical trials. So this is sort of an example of, perhaps a clinical trial from clinicaltrials.gov that we're perhaps all familiar with, not the specific trial, but just sort of the general format, that really comprises, a couple different parts of classic like inclusion, exclusion, some other things about the trial itself. And, for many of us on the machine learning side, you might be looking at this and thinking, hey, a lot of these look like logic constraints. Could I actually just go ahead and say, let's use an LLM to try to derive from this like a set of logic-based constraints. So go from the text, provide some sort of prompt looking at it, and end up eventually with something that looks a little bit more like this, like your standard, DNF sort of notation of ands and ors and nots and things like that. And I think the thing that's really interesting about this and sort of this initial proof point from a couple of years ago that really struck me was that there have actually been a lot of tools developed in this space to do specifically this type of extraction. And so, as somebody who is more deeply entrenched in sort of the NLP side of things, I was actually quite surprised to see, some of these LLMs, the one that we're looking at is GPT, but there are many others as well, of course, we're already not only competitive, but at times outperforming a lot of the sort of dedicated heuristic-based tools that were developed for this space. And this was a really interesting sort of point for me, I think, in part because it also got us thinking quite a bit about, not just this biomedical tech space, not sort of just clinical trials, or, maybe you can make an argument that, for example, like the text that appears in a clinical trial is well structured and sort of nicely formatted, and it has a lot of these sort of niceties that you don't typically see perhaps in clinical text. Maybe you have a discharge summary that's really heavily structured, but you have nursing notes that are sort of the equivalent of tweets in length and quick updates or something like that. And so maybe it's really just a reflection of, well, this actually wasn't as hard a task as we thought it was. It's actually something where a lot of that data was already sort of structured as this logic-based output. And so we really started looking at, especially in the cancer space, and I'll clarify at this point also, I'm going to show a handful of things during the course of this presentation that look like patient data. None of them are actually patient data, just for to be really clear, and I'll mention that for a few other times where it looks like patient data as well. But again, just to be clear, nothing is actual patient data. So if you consider sort of on this clinical side, what things might look like, this is maybe an example of patient data where you actually have lots of different types of notes taken across a whole bunch of different settings and time points, right? And this is just a tremendous amount of information. It's not nearly as concise as something like a clinical trial. And it has lots of different types of sort of substructure within it as well. So it's sort of interesting from like a linguistic standpoint. And so we started thinking, of course, similar to the exercise that we had done with the, this initial research in the biomedical space, could we do something similar in the text space? And we looked to specifically do a model that would identify sort of key cancer staging attributes. So things like clinical TNM, pathological TNM, all these things that sort of tell you a bit about like tumors, sizes, metastases, all these things are sort of bearing on a number of outcomes or useful for various registries or research endeavors, right? And I think what was nice to find initially was that, yes, we were able to do this, but, it took, not a trivial amount of effort. It took, some effort certainly on sort of this like per attribute basis, perhaps. But again, I think really the takeaway for us was this is actually like an interesting and quite promising direction from these sort of preliminary results where you can effectively imagine going from sort of automatically reading a guideline and then extracting some of that information in a sort of zero-shot fashion, right? And so this led to sort of a broader exploration, which was, if we can imagine doing this on sort of like a per attribute basis, could we actually expand that into sort of this notion of universal abstraction? And so this is the paper that I mentioned earlier that I think looks like we submitted it on a few days ago. So I think at this point, probably up on archive, but if not, we'll be sort of imminently there. But the idea behind this was really, can we take some of these large language models and leverage that sort of structuring ability specifically to try to scale some of the existing attribution, like annotation and abstraction processes that many hospitals have in place already. Another place where this is really particularly interesting is perhaps when you have guidelines that change over time. So you have, for example, a definition of some, I'm struggling to come up with a specific one right now, but there are many different examples where maybe the clinical guidance on how to identify a specific condition or a specific attribute is actually shifting over time. And in part because of that, what ends up happening is you want to sort of retrospectively understand and extract that information to normalize or perform some form of research, right? And so there are a lot of different sort of possible outcomes, whether it's sort of like the direct abstraction exercise or alternatively to sort of support some of these downstream sort of registration and research tasks as well. And so this led us to sort of this hope, whereas previously we were doing something like this, where we say, okay, well, we have this conventional approach where you say, I'm really interested in, T, I'm really interested in N, I'm really interested in M, like define each one of them, try to extract each one of them, derive a separate model for each one of them. Could we, for example, rather than, doing this sort of conventional approach of treating everything sort of as a, individual model, maybe with sort of human in the loop to provide some form of interpretability, could we just sort of leverage this general sort of flexibility that's apparent in a lot of prompt engineering exercises and build out sort of this universal abstraction notion? And so this is in the work described as UniMet abstractor. And I think this is a really interesting and sort of promising space where you can effectively say, let's identify what those meaningful attributes are for us. And then let's try to sort of run that through and actually get some of that structuring out the other side at scale. And of course, I think part of the expectation here is medical abstractors maybe are the gold standard in this case. Certainly their performance might be, significantly higher, but at the same time, the time that it takes to do that abstraction is also significantly longer. So if, for example, you're sort of making this decision around, hey, we could actually, abstract maybe 1,000 patients worth of data, but it will take a year. If you could abstract that same 1,000 patients, but it will take a day, are you willing to sort of tolerate that trade-off in maybe a little bit lower performance, for example? And so we really looked at this by initially just sort of doing some of the existing tasks that we were interested in before. Like one of the reasons that we were actually really interested in some of the things like clinical TNM or pathological TNM is there were actually these really complex cases where you had information that was spread out across a record. And so there were these sort of like these long context attributes that we were interested in, specifically where they were important for cancer staging, but presented sort of unique, interesting NLP challenges. We also wanted to sort of look at this just for shorter context attributes. So things like PD-L1 biomarkers or performance statuses or treatments that have been sort of looked at. And I think what's again really interesting is this is the type of information where I think we all know it exists, but it's not necessarily structured, right? In some sites it might be structured, in other sites it might not be structured. It's sort of what has sort of grown at that sort of local site. And so being able to do this quickly and at scale actually offers, a lot of new opportunities with respect to both normalization, with respect to reporting, with respect to accelerating a lot of the research that we might all want to do. Because again, I think the thing that I recall most heavily from some of those prior conversations was when working with clinicians, they maybe have this research idea in mind, but they're faced with this, pervasive challenge that they don't have the structured data for it now, so they can't do the analysis they'd like to do. And they have sort of two options at that point. Start collecting the data now and then wait until there's enough data in the future to be able to do that analysis. Or hire a team of abstractors or themselves or students or whoever they can find to sort of volunteer time to retrospectively go back and identify meaningful patients and then extract that same information to do the study on a shorter timeline. And neither of those is necessarily a great option. So this is minimally a great way to sort of test out some of those proof points. And I think what was quite nice for us that we were able to see was we performed a couple of different baselines, specifically things related to sort of heuristic extraction, which had been used quite extensively, to really look at how can we actually, like, how are we doing relative to some of those baselines? And I think the sort of nice thing here is we don't see significant regression, but we do see sort of improvement in that overall precision recall curve. And it also happens much, much faster, both with respect to sort of like the actual like inference, but also with respect to how long did it take to sort of define some of those specific criteria for those attributes, right? So rather than developing or spending that sort of upfront time on developing a model for each one of those attributes, can you, instead of spending a couple of weeks, maybe developing a model that works and testing and validating it, can you spend, a day maybe or a couple hours just sort of getting something to stand up and sort of run immediately? And so just to sort of dive a little bit into like what the intuition behind this work was, although again, I think now that the paper's up, the details are, or will imminently be up, the details are largely there. We really approached this sort of from three places. So the first one was we wanted to allow for sort of as much structure as we could provide sort of upfront. So there's sort of these parts that are effectively like predefined. We really wanted to have the users have sort of this like user input space, both with respect to the data, of course, but then also with respect to how do you define an attribute? Like how do you define like what is your definition that you're looking for out of the treatment or the specific type of treatment that you're looking for? And then also provide sort of this notion of sort of like optional additional supplementary information. So specifically, if you're defining something that has a clinical guideline, just what's the guideline? Like we'll help sort of automatically summarize that guideline so that it can be used in the context of the prompt. Do you already have sort of existing data? For example, is this something where you are trying to extract information, but you have some close correlate in a registry somewhere? Providing that sort of information specifically so that you are able to much more rapidly actually do some of that structuring on the sort of note by note basis. And so, what this looks like for some of the short context attributes. So some of these ones that are maybe easier. And I think really by short context, the context here is really, how much of a record do you need to see? Is it really that you need to see sort of like a patient level notion of sort of what's there, or is it sufficient to actually just sort of look at a single note perhaps? And I think what's really nice about this is it sort of gives you that flexibility maybe to work across both these sort of shorter attributes where you can just quickly say, here's the attributes I care about, I care about these three things and define each one of those and then try to do that extraction process. Versus, for example, perhaps something like a longer context window where you're effectively saying, hey, this is, clinical TNM. There are guidelines written about how to identify each one of these that are specifically provided for medical abstractors on how to do this task. Here's how a human would effectively do this task. Here's some additional guidance and allow for that sort of interjection of additional information. And I think, just to try to ground this back to, sort of maybe like reality before we maybe move on to some of the multimodal pieces. I think one of the things that's actually really interesting about this and the ability to do this quite well is that when you're able to take sort of that information, both from the biomedical text, so from things like, clinical trials or other literature that exists in this sort of medical context, and you're able to sort of quickly scale and scaffold that same information on the clinical side, you open up a lot of opportunities with respect to, for example, with literature and clinical data, things like reproducibility or validation at larger scale than was done in like an initial study for meta-analyses. But then you're also able to do things like actually do that sort of outlining between, for example, like patients and corresponding clinical trials. And so it gives you sort of these additional points of evidence that you might be able to scale pretty rapidly. And I think one of the things that, was sort of motivating us originally is we were hoping to, and now have, I suppose, been working on things like this, where again, none of this is real patient data. But the sort of example here is looking at, can we quickly structure a whole bunch of information that's not readily available within a patient's record from notes? I'm sorry it's scrolling so fast. It's actually a little disorienting how quickly it's scrolling, but can we quickly structure some of that information? And then can we take that information and identify sort of corresponding clinical trials where that information is relevant and try to facilitate some of that actual matching process? And, I think I'm going to advance to the next slide just because it's scrolling so fast, but maybe just a few thoughts about, what that actually means. I think what's really interesting about it is that, there's an opportunity really to sort of expand what it means to have clinical trials, right? Like in some sense right now, we are often bound in a clinical trial sense around, what is, as a patient, I have a whole bunch of information, I've generated tons of information, but the trials that I'm eligible for are a combination of what trials exist at my site, and what trials are my care team aware of, basically. And I think, having the ability to much more quickly expand the pool is interesting, both from, the standpoint of, perhaps some of the companies trying to run these trials where there's a exceptionally high failure rate. And then also from the standpoint of the patient, where they don't even know what they're eligible for necessarily. They don't know the full set. And so really being able to empower them and say, this is actually the full set of options that you at least seem quickly to meet the eligibility criteria for, opens up some of the potential. And in the cancer space that we've been looking at, those are incredibly meaningful options really to have. So I'll sort of put aside a little bit of the NLP part, as much as that is very much my sort of history in this space. And I'll sort of start, talking a little bit about some of the expansion into sort of multimodal and some of the proof points that we've been looking to develop there, because I think that's actually one of the most exciting things about this broader context of generative AI in the past year or so. So I think, unsurprisingly, this is actually now even a little bit out of date because there's other entries here as well. But effectively, the thing that's really interesting is we've seen this, progression across various benchmarks. Things just keep getting better and better from this language standpoint. And, there's all this discussion of emergent capabilities and things like that. But I think for us, the maybe takeaway is really a lot of these frontier models, a lot of these, models are just surprisingly proficient at biomedical text. And that really surprised me, in part because, I think for a long time, it was really this case that you would only expect something to do well if it was sort of trained on similar things. And a lot of these models haven't seen a significant amount of clinical data, certainly, but they sort of see this translation to clinical settings, in part just because of in-context learning being, as powerful as it is. One of the things that's a little bit concerning, though, is if we go back to sort of this picture of, like what a patient record might look like, it's a little bit misleading because as I presented it the first time, it's really focused, just on text. But of course, as I said earlier on, like, actually all these patients are actually generating tons and tons of different types of data. Especially in the oncology space, you often have pathology, you have, tissue samples that are taken, things like that. You have often radiology, increasingly omics. You have all of these different sort of points of evidence for how we might look to sort of contextualize that patient, but we certainly don't want to throw them out. And I think one of the things that's emerged as a somewhat concerning finding here is that same sort of proficiency that we see in the text space doesn't always sort of translate into other modalities. And I sort of I like this example to some degree, in part because this is looking at what if you ask for a photo of a CT, like a lung CT scan, right? And maybe barring that one on the lower right where it's maybe not human or just totally out there. Many of these are sort of, they're like cool pictures. Like they're great if I wanted to throw something into a slide deck and present it and things like that. But I think every clinician will tell you, like, none of these are even within the realm of plausibility, right? Not only are they very far from this sort of corresponding reference example, but like they don't have any of the hallmarks of any of the common imaging tools that we actually use. And so they're just totally impossible, right? Like they don't pass, this sort of artificial Turing test, perhaps. But there's this hope, right? That like, hey, we saw sort of these improvements in sort of the text space. Could things, really be rectified by sort of continued pre-training? And, it seems like, even though there's sort of this growth opportunity, there are some directions that we can try to focus on here. And I think, at this cutting edge of lots of different modalities, there's basically lots of different exciting research directions. I'm, maybe putting this up here mostly because I think for some of the folks who have joined, you're probably working in one of these areas, and I would encourage you to work across some of these areas as well, but also really drive improvements within these areas, because I think it's actually going to end up benefiting all of us. But one of the sort of challenges that we've often run into is, this challenge of combinatorial explosion, right? Like if you think about what it would be required to train sort of like an early fusion, like joint model across all of these, it's really, really challenging, minimally from like a computational standpoint, because as you sort of introduce that additional form of information, you're going to need some like really interesting training dynamics and things like that. But actually what's really sort of interesting here too, from a healthcare standpoint, is that, we know from, really great work from, Griffin Weber and a bunch of others over at Harvard DB&I, now I was going to say maybe it's definitely more than 5 years, maybe 10 years ago. I think when you start applying these filters for who has complete data, you start to really quickly winnow the pool of patients that are available. And it, more concerningly, really biases that underlying pool as well, right? So, maybe as expected, you end up with often older patients because those are the ones who, tend to have more interactions with the healthcare system and in turn more healthcare data. But you also bias it toward other demographic features, and that doesn't really seem like a good thing to have, if we're thinking about sort of this combinatorial explosion. And so I think in addition to sort of maybe some of the compute related considerations, there's very practical considerations for why we might want to sort of focus on like late fusion models in the context of healthcare, just in terms of getting sort of, a representative cohort, for example, in each of these areas. And that's really, maybe been sort of an underpinning to some of the work that we've been doing, in part because, like I said initially, my background is text, and so I'm much more comfortable with text latent spaces than many others. So that's maybe the part of the reason. But I think the other reason really is often in healthcare, we really have a lot of text co-occurring with some of these other modalities. And so you can imagine, sort of this like maybe like conditional dependency trick from, a while back of let's try to like actually remove some of these edges, and rather than focus on sort of this large joint model, can we start to really focus on just those sort of pairwise, those sort of pairwise pieces. And I think there's a very real open question here about like could text actually serve as this effectively like an interlingua, right? That would both simplify our learning but also be advantageous from a healthcare standpoint. And there's a lot of different reasons you might really be able to expect that it would work for this. But I think the primary really driving reason is actually just like I said, that you actually often do really have lots of naturally co-occurring pairs with text. And so that really effectively allows you to focus for any given modality, if it's, radiology or pathology here, on this idea that, you could really just create sort of encoder-decoder models, for example, for each of these individual modalities. And what's appealing about that, in part, is that you can do this sort of modality-specific self-supervision, right? So you can sort of take some of the intuition that you have about a sort of specific modality, or some of the inductive biases that and sort of bake those into models that sort of broadly fit this sort of like overall architecture to create sort of multi for this more limited definition of multi that means exactly two, within sort of a specific modality, paired with text. Then after you've sort of gone through and created some of these specifically like encoder decoder models, maybe I'll call out a couple. There's things like maybe like Dino for radiology, or some other work that I'll talk about a little bit later on. You start bringing back this notion of like well, how do we actually bring this back specifically to some of the proficiency of the LLM, and so we don't want to throw away some of those text pieces. We really want to be able to get the best of every one of these worlds. We want to have the best of the sort of modality specific, but then also this sort of best of things like GPT, both for the sort of discourse aspect of it, but then also for the sort of representational power that it sort of carries from the broader general domain. And I would argue actually like we actually already have many not just us, but like across the community, we have many state-of-the-art models for things like, radiology. I'll talk a little bit later about pathology, because I think that's actually been one of the most exciting spaces this last year, things like proteins. And this is really where we can effectively sort of start to inventory out these different modalities that we care about, and then sort of piggyback and get for free some of the benefits of the underlying frontier models that we're training. And, again, like I said before, like concretely, the sort of intuition behind this is create modality-specific adapters that serve as sort of this translation layer for grounding the modality, like any given modality, into that sort of text representational case. And so, in this case, we really are looking to ground multimodal patient data into sort of this common text space, specifically for the capacity of reasoning. And it, like I said earlier, it maybe is not perfect, because I think there's a great question about like, is the text latent space actually sufficient to represent human physiology? Like maybe that's not the best base representation, but maybe it is actually good enough, at least empirically, to come up with some really interesting things that then facilitate sort of like fine tuning and sort of like continual pre-training and things like that. And so I'll sort of start with like an interesting example here, in part because it was actually we just managed to publish it this last year, Although the model itself, we actually released pretty early on in 2023, where we were looking at this idea of building out effectively, a CLIP style model, so like a multimodal model for image and text. And specifically what we wanted to do was sort of leverage some of the work that we had done previously in building things like BioMed for example, or some of these like LLM-based models, and sort of expand that to sort of this multimodal setting. So we took a similar tack where we looked at really, can we go through large resources in medicine, like PubMed in this case, and can we identify all of the sort of like image text pairs, so primarily figures and corresponding captions, do a bit of work to sort of, especially for, multi-caption and multi-figure figures, subfigures effectively, can we sort of split a lot of those out and build out a nice corpus to learn something that is proficient for biomedical multimodal models. We were able to do this, reasonably quickly and get this sort of out to everybody to use and sort of build on. And I think what's been, was pretty exciting and sort of that initial follow-up immediately after we made the model available was there was a lot of community effort around building both similar models, but then also expanding the data sets that were available as well. So, I call out a few here, things like, Clip that leveraged sort of Twitter as an underlying data set, Quilt, which used this tremendous amount of medical information that exists on YouTube that I didn't even ever think to look for. Conch, which also used PubMed Central, but then also relied on some medical textbooks that are like very high quality information and have sort of these concise summaries. So a whole bunch of sort of different types of things that really sort of, again, expanded within that single modality, the availability of offerings for modality and text pairs. I think what's, of course, I've maybe omitted so far and alluded to in the adapter piece, but didn't really elaborate on is, how do you go from a model like that back to grounding it against specifically, an LLM? Like, how do you actually integrate this with an LLM? And so we looked at this initially in this work called LavaMed that was really looking at this broader Lava architecture, which is this, I would say, pretty flexible and somewhat generic architecture where you're really looking at, can I build an image encoder and some sort of corresponding adapter, and then can I pair that with a text decoder, right? So in the specific example of something like, LavaMed, it's a relatively simple thing. It's you take some of the biomedical clip as your sort of image encoder. You take initially Llama, but then afterwards Mistral as your sort of like LLM basis, and you sort of do this like linear projection into the sort of latent space. There's a bunch of different formulations of this, and I think if you look back to maybe to last year or the year before, things like MedPalm or MedFlamingo actually is also a great example. They all sort of use different formulations, but that same, for example, like a different projection, like a Flamingo, I think uses gated cross entropy, and so there's sort of like different sort of formulaic pieces you can build out there, but that underlying formula, of really how do we do this concretely from an architecture standpoint, and then build out sort of the corresponding instruction following data using our LLM. So in this specific case, what we did is we built out a ton of sort of multimodal synthetic data by saying, you don't get any access to the image. You just sort of get the caption. What are a bunch of questions that could result in this caption being the answer? And that's sort of the basis for this sort of synthetic instruction following data that allows you to sort of continue training a model like Lava or any of these sort of other similar models into sort of a biomedically oriented model that sort of leverages both that sort of encoder that you've created and then also the sort of corresponding under LLM tuned a little bit more closely for that biomedical space. And so I think, maybe just to highlight it, it's a little bit, from last year, but I think still actually quite useful just in part because it's open. There's a LavaMed 1.5 that's up on Hugging Face. And I think actually throughout a lot of the work that our group does, we have focused pretty heavily on, trying to make as much of it as possible available broadly and ideally in easily accessible formats as well, so that it's not just something where, people have access to some of these models and other people don't. I think we are very aware that, we are all in this together, and the way to sort of advance the community is by helping the whole community advance as well. And so, even though this is sort of an interesting thing, I think one of the things that was really exciting about sort of LavaMed, that's like 1.5 release, is that the actual release actually only uses a small fraction of the underlying biomedical data. So we had these roughly 46 million pairs, and for that instruction following piece, you only actually need a small portion of it. And so I think when we sort of did this initial endeavor, I think one of the things that was really exciting about it was, hey, can we sort of use that same formula in a bunch of different places? And so we started looking at specifically things in radiology and thinking to ourselves, hey, is this actually something where we can sort of do this maybe for each one of these different modalities? Like do sort of something specific for radiology, do something specific for some other modality as well. And we quickly found that actually, yeah, we have a ton of different radiology image report pairs. Some of those are of course part of that broader biomedical set that we could pull from PubMed, but there's tons of different examples and data sets that exist, broadly that have these sort of paired data. And so we looked at, what happens if we sort of train this thing specifically to be, proficient for radiology. And maybe unsurprisingly, perhaps because I'm, showing it does very well, which is quite nice. Specifically though, what you end up seeing is that relative to like a vision capable version of GPT, a sort of generic maybe model in the space, our baseline being Lava, does very poorly because it's never seen these types of images before. But when sort of tuned in this sort of specific way and adapted, using this sort of specific encoder decoder, you can actually attain pretty high performance that quite quickly surpasses even what's available in some of the sort of vision-enabled models that are out there. And so I think this is actually like the basis of a lot of really exciting work, things like other group from Microsoft Research, things like Myra, really exciting sort of extension of that, especially with respect to grounding. There's been some really awesome work from the groups here at MIT on things like PathChat, just to call out a few. But it also brought up a bunch of these questions about sort of evaluation, and I think that's really, this sort of recurring question now of if you can generate and answer questions at scale, how do you actually evaluate them at scale too? So I think maybe, pausing there, I'll sort of go on to a couple of examples and try to, wrap things up concisely enough so there's time for questions. But I think this, taking this formula and sort of adapting it in different ways has yielded interesting results as well. So one of the next things that we tried to do was, rather than just saying, let's do this sort of like image encoder adapter and then sort of anchor it into the text decoder, can we, for example, combine two encoders and really have a single sort of image-based decoder that sort of works to, in a similar way, but like, again, slightly different formulation. And I think this has been really interesting because it allows you to do a couple of different things. One of them is Biomed Journey in particular allows you to work across a great number of sort of different types of tasks. So you can ask sort of these open-ended questions of, segmentation or object detection or whatever else it ends up being, and sort of start getting sort of answers related to it. But it also lets you do some interesting things related to sort of counterfactual image generation. So in that sort of, this is sort of like one of the classic examples that we were using, can you have sort of a prompt that says, enlarged cardiac silhouette or resolved pleural effusion or whatever it ends up being, and start to see sort of the generation of that sort of image that allows you to specifically see some of the changes that you're asking for as well. But that prompt, of course, in some cases can be sort of changes in conditions, but could also be, identify this area or help me with some form well, it forms the basis of something that would allow you to then go on and sort of do that parsing task. And so in turn, this actually resulted in sort of our endeavor to turn this into using a mask decoder. So again, a slightly different formulation rather than sort of, just that sort of like image decoder. Can we do this sort of mask decoder, this image parsing task? And so this is sort of an interesting reformulation that sort of came up last year, really around how can we take some of the sort of underlying image tasks, and rather than have separate models for them, sort of unify them into sort of like instruction following style prompts that allow us to do many different imaging tasks with sort of a single model. And the sort of example here, I think is pretty interesting. And there's a site that you can sort of go to see some of this and maybe even play around with it a little bit. But the sort of nice thing about these types of models is it sort of opens up this gateway again for a lot of the clinicians who might just want to ask for a task or might just want to have sort of a quick probe to be able to say, can I do this task, in some sort of, quick sort of way? Like, can I identify this thing and sort of get immediate feedback about whether or not they're actually able to do that, in a reasonably fast sort of way. And maybe where I'll wrap up, just looking at time here, is really around maybe this last space that I mentioned that I think has been really exciting over this past year in sort of digital pathology. We were looking at this with specifically some collaborators at Providence Health. I think one of the things that's really unique about sort of the scope that they have is they have, obviously in this Boston area, there's a ton of hospitals and DFCI and places as well. But, I think what's really exciting about some of the resources they have is they have a really large, population that they're sort of able to study. They have, many, many patients already sort of with genomics. They have tons of different sort of studies with radiology as well. The number here, 600 million, is pretty tremendous amount, and also have, this enormous volume of sort of digital pathology, which I think one of the reasons I've been most excited about this space is really this idea that, it felt like even 3 years ago, perhaps, many of the conversations that, we were having with folks in pathology was really trying to encourage them to even move to digital. And so I think this, if I think back to what that transformation looked like in radiology, it came very fast in radiology. It came very fast. It just took a little bit longer, perhaps, in pathology. But I think there's some really interesting things about pathology, specifically, especially with respect to the computational aspects and modeling as well. Notably, that the image sizes are often absolutely enormous. If you're happy with sort of carving something up into smaller segments for sort of your traditional radiology, you're faced with a whole different computational problem when you have maybe 100K by 100K image, and it doesn't even fit in memory on the largest memory things you have access to. So it's really just sort of a unique space that I think is both exciting from a computational standpoint, but then also from an impact standpoint. And so we looked at a whole bunch of different sort of tasks here, but I think, again, just maybe to skip around a little bit for the sake of brevity, I think one of the ones that was quite exciting was really, if we look at sort of like the slide level, so there's sort of, different types of tasks, maybe at this sort of like sub-slide level and then sort of at this sort of slide level, we're able to see state-of-the-art performance on cancer subtyping and then also on gene mutation prediction. And, these are sort of actually like quite concretely things that are exciting for the pathologists that we're working with and can support some of these sort of like pan-cancer predictions that we're looking at with them. It's also exciting because it sort of alludes to this idea that you might be able to start uncovering potential genetic pathways as well when paired with some of that corresponding information. And so I'll again, sort of note that this is another model that was born from this sort of collaboration with Providence and also a close collaborator at University of Washington. And I think for me, actually, in part, one of the most exciting pieces is really, it's also another example of a model that we're able to make, publicly available for everyone to use. And so I think this is, a great reflection of some of the sort of leadership that Providence has in terms of making some of these resources actually broadly available to advance the sort of broader research agenda of our community. And so I guess, like I said, with brevity, with that, I'll also thank, the many folks on our team who actually made this, really truly possible, and also made deciding what to talk about today incredibly challenging because of how much they do, and many of our collaborators as well. And I'll maybe end there with a few minutes to spare.
Great. Thank you so much. Why don't we open it up to any questions from the group? Oh, there's already one in the chat. So the question is, can you please comment on the degree of performance gain between number one, training a new multimodal model from scratch versus number two, integrating other modalities into the knowledge distillation?
Yeah, I think, or actually, okay, so I guess on the one hand, maybe it's a challenging question to answer without context for like what data might be available. I think in part, so for example, if you didn't have a lot of data available at your like local site, you would sort of expect that training a new model from scratch might not yield something very relevant, at least, but by comparison to some of the things that are maybe already out there. And so in that case, maybe you would lean more heavily toward sort of these other modalities, or integrating some of these other modalities into the knowledge distillation piece. On the other hand, if you do have access to a tremendous amount of data, there might be actually quite a bit to gain from sort of training a new modality from scratch. I think at times this is an empirical question. So I would say maybe just take this as sort of general thoughts, but if you have sort of like a concrete use case, reach out and I can try to answer for your specific use case. I think that maybe the other thing that's sort of interesting and is becoming maybe an interesting consideration is that I think, for quite some time, in the machine learning community, we have sort of a notion of like generalizability and what that means with respect to a model for out of distribution data. In the clinical setting, there's another notion of generalizability that has to do with sort of multi-site validity and things like that. I'm wary to say that maybe the two, or maybe what I'll say instead is the two are not always as closely aligned as maybe we might like. And so I think there's several cases, of course, where, some of the machine learning tooling that has been sort of created doesn't sort of generalize. It generalizes maybe with respect to sort of the machine learning notion, but not necessarily with respect to the sort of like clinical expectation or notion there. And so I think especially in some of those settings, and as we think about, how much data do you really need, there is a really interesting question about, I think in the ideal setting, of course, we have sort of this sort of federation or consolidation of data, perhaps, that allows us to generalize very broadly. But in absence of that, at what amount of data is sort of sufficient locally to see sort of the performance that you might see elsewhere as part of it as well.
I had a question about kind of some of the attributes that you're extracting from patients.
Yeah.
Are you ever interested in extracting kind of an overall summary of a person's medical history and maybe picking out the most salient time points or events that might have happened to kind of get a broader picture of someone's history relative to maybe cancer or some other important factor?
Yeah, I guess so. There's great work in that. We have not done as much work in that space. There's some great work in sort of summarization. I'll maybe call out some of the work that maybe like Noemi Alhadad's group had done, like Griffin Adams there, and Emily Alsenser at Stanford had also done a ton of summarization work among many others who are really working in this space. I think that's a really interesting area that would be very interesting to explore, in part because as I think many of us are familiar with, one of the most bearing sort of things on patient outcomes is actually like patients' engagement in their own care. And able to sort of do that summarization quickly for a specific clinician is actually quite useful, I think, in both sort of supporting that care, but also driving some of the conversations that might be more bearing on outcomes than some of the other factors that we often consider.
And then we had one more in the chat. Thanks for the great talk, it says. You alluded to methods for evaluating generations at scale. I'm curious to know if this is a problem you're actively working on and what your broad approach might be for evaluating generations at scale.
Yeah. So I think this is so there is some ongoing work that we're doing. I don't have any of it in this deck, so I can't pull up slides or anything like that. What I will say is I think there's this challenging question among the NLP community of that vaguely resembles this question of like, can you evaluate your tools using your tools? And it's a little bit tricky because obviously there are lots of places in computer science where that happens, right? I think there's actually like a history among systems designed to specifically build your compilers using your compiled languages, and there's like a whole bunch of places where you might want to do this. It's a little less clear, and I think just maybe thinking back across several review cycles, it seems like there are often these cases where specifically you might be really compelled to evaluate your tools using other LLMs. I think maybe minimally it would be very useful to use several different LLMs as opposed to maybe just the same one. But I think there's this. I think there are. I think what I'm really trying to say here is I think there are ways to do it responsibly in a scientifically grounded manner, and that is unfortunately not what we always see. And so we should be, be a little bit wary of it as well. Oh, I Danielle, I think you're muted. Wait, am I muted? Wait, I think you're muted.
I'm muted. I'm
Okay.
sorry. I'm sorry. So yeah, there was one last comment from Peter Solovitz saying that summarization is a great application, but there are groups that have shown that although the summaries are great, maybe 90% of the time, they're also terrible 10% of the time, which is not still not good enough for real practical use.
Yeah, I guess for those of you who don't know, he was also my thesis advisor, and as Zach at I think one point pointed out, it always brings you right back to your thesis, perhaps getting questions. But I think that's actually a great point and really speaks to what is actually the sort of necessary level of performance in any of these sort of evaluations in order to have sort of relevance in clinical settings. And I think this specific example that Atul's group had done as well really shows that I think for many of us from a machine learning standpoint, we started seeing 90% on sort of anything, we'd start wondering, is it time to move on to the next task? But there's obviously this tremendous amount of work that actually has to be done, getting from 90% to that sort of epsilon from 100% sort of performance in order to make things actually grounded in sort of the reality of care as well.
Great. All right, we've hit 3 o'clock. So thank you very much again, Tristan, for the really lovely talk. And then for everybody else in the group, our next ML4H talk will be next month. It's always the first Wednesday of the month. So Wednesday, March 5th. And the talk will be given by Can Lee from UT Health Houston. And she has some work on fairness and other aspects of machine learning for health. So hopefully we'll all see you there. Thank you very much, everyone, and see you next month. Bye.